Jose. It's something you have to accept. Okay? We can try to do PLSDA now. Before doing that, okay, remember then you can look at the variable importance. Okay, here we have just 5 variables, okay? But we can have a estimation on which are the most important variables, okay? These weights are always positive, okay? So this means that variable number 1, for example, okay, in random forest is the one which has more capacity of discrimination between the classes, okay? Okay, this is for the variables. And on samples, if you go to results, random forest, predictions, the only thing you can get is the probability of a sample to be in a class. Do you remember? Okay, we predict a sample on the basis of a average, a consensus. Okay, so if all my trees predict a sample to be in one class, the probability will be 100%. Okay, to be in that class. If one sample is predicted by half of the trees to be in the blue class and by the other half of the trees to be in the red class, then the probability will be around 50%. Okay, so here I have the situation let's say as a function of this probability. Okay, so for example, this is the probability to be not bioaccumulable, which is the blue class. Of course, the majority of the blue samples have higher probability, but you can see there are some red samples which of course are those which are misclassified. Okay?
Davide?
Yeah.
You could use that plot to calculate the rock cubes, for instance?
Yeah, you can. You could. Yeah. You move it. Of course, when you have probabilities, then you are free to use it as you want. Okay, so if you want to be more strict, you can say, okay, I will classify a sample as not bioaccumulable only if the probability is higher than 80%. Okay, so then you can change the model as you want. Yeah.
And what about the unbalance in the classes?
Yeah, these are unbalanced.
How does this affect the model?
I think in this case, the red class, which is the one which has the highest error, okay, is the one which is less represented. So I think this has some affection in the model. Okay. This is the red class is the bioaccumulable and is the one with the lower sensitivities in cross validation. So I think this has an effect. Okay. But this is something we cannot change because it's less represented in the chemical space. Yeah.
I've read in some papers that what they do is to reduce the number of samples in one of the classes.
In the blue class?
Yeah. What do you think about that?
I don't know how to do that.
I mean neither, but I read it.
I mean, probably you can do it, but you have to repeat it many times.
Kind of on a bootstrapping stuff.
Yeah. You have when you have unbalanced classes. I have read things, and one way is to balance the classes by reducing or by duplicating samples, but still you have them to repeat stuff many times. Yeah. Okay. You want to do PLSDA?
Yes.
Okay, let's try. So if you do PLSDA, okay, here it's better to auto-scale the samples because you have very different, variables have very different scales, okay? So we can auto-scale on the columns, and then we can look for the optimal number of latent variables in the same way, doing cross-validation, so we can do optimal LD. Okay. How many latent variables you want to use? 3? I mean, it's very similar. Eh? Let's try to do, when I get this, I try to do cross-validation with a different number of groups. Maybe we can do cross-validation with 3 groups, optimal number, latent variable, 2. Let's try with 2 latent variables. Okay? Okay. Calculate. Okay, this is the error rate and error rate in cross-validation. We can have a look here. Still we have the same issue. Okay, with PLSDA.
But it's not overfitted.
It's not overfitted. Error rate it's strange because cross-validation is a little bit lower. No, it's the same. Yeah. Then what you prefer?
Yes.
You know what? The final call is the test set. Okay? We have a test set. So now we have a PLSDA model with 2 latent variables. Okay, here we have the PLSDA, so we can clear the data, we keep the model, we load the test set, and we predict the test set, and we will see who wins. This is PLSDA versus random forest. So we load the test set. If it's PLSDA, you pay the first bill, this is random forest, I think. Class test. Okay, we load the test of the test samples, and then we can predict samples. Okay, if I'm too fast, tell me. Okay, it's okay. So predict samples. When we can go to the classification measures. Okay. And you have training, cross-validation, and here you have the test set, okay? And I have to admit that this is not overfitted, because on the test set you get a very similar situation. So you know that here you have a problem with the bioaccumulable class, and this is the actual status of your classification, okay? This is PLSDA. So 65% more or less, okay? Now we have to clear everything. We have to reload the training set because we didn't save the random forest model. So we load the training set, we load the class of the training set, class train string. We calculate random forest. We use it 1000, right?
Yeah.
Okay, let's keep cross-validation. Maybe it's better to add the wheel.
Nah, the weight bar.
Yeah.
The annoying weight bar.
Okay, we can clear the data, we can load the test set, we can load the class of the test set, and we can predict, okay? And we can go to classification measures, okay? And it's very similar to what we get in cross-validation. So I think the meaning here is that somehow you overfit a bit the set. Here we get an error rate in cross-validation, on the test set is 15, okay, it was 20 something with PLSDA. And then sensitivity on the bioaccumulable class is around 80, okay? then you decide, okay, on the basis of what you like. Okay? So this is how a random forest can work. This is the very, very basic approach, okay? But as you've seen, I mean, here I have only 5 variables, and it took how much? 10 minutes to optimize, okay? When with the Raman dataset, it took the whole coffee break, okay, to optimize. If we have bigger datasets, I don't know, a lot of samples, a lot of features, then it can take much time. And if you want also to optimize other hyperparameters, then you have to repeat all the procedure many times, so it can take hours, maybe one day. I don't know if you want to really go to very, very specific tuning of parameters. Okay, questions?
I have one. Can you combine other variable selection methods with random forest? For example, in the case of a spectral dataset.
If you want to complicate things, yeah. But I mean, here you already have a kind of selection of variables.
Yeah, but I mean, if you previously perform a variable selection, your models will change or not?
If you previously, yeah, sure, of course, I think.
Because
I
somehow
don't
random
know.
forest is.
I mean, if you, I have no idea.
Okay.
I mean, of course, if you limit the number of variables, your model will change.
Your model will?
Change, yeah. But I don't know, doing a variable, then it takes a lot of time to run a model. So doing variable selection,
Mm-hmm.
it's going to be, I mean, in a computational point of view, not easy. And it's somehow already CART is somehow a variable selection method. So I don't know.
Yeah, but I was thinking on the previous dataset, the Almond dataset.
Mhm.
So maybe if we previously select a smaller range, spectral range, in which I don't know, it was just one peak, right?
Yeah, but then on that data set probably CART doesn't work.
Yeah.
Because there are many features and it takes a lot of efforts to. Let's try. So let's do one thing. Do you have any further question on random forest and this case study? No? Okay, let's clear the data. If you go back to the data folder, we can select the Almonds dataset, which is a Raman, you explain it, it's a Raman spectra of
Raman spectra.
80 more or less, 80 samples.
Mm-hmm.
And the classes are sweet and bitter.
Yeah.
Okay. And we go back to the toolbox. Okay. We can load the training set and we can load the class of the training set. Okay, I already tried to do random forest before without optimization, and it was clear that it didn't find the correct variables. Okay,
But maybe it was a question of pre-processing the data.
but random forest does not depend on the pre-processing.
What?
No, because you look at when you do CART, you don't you just look one variable at a time. Okay, so you don't have that issue.
You don't have the scale trace.
You don't have the scale problem. You just look one variable at a time and you look for a threshold.
But you might have problems with the baselines.
Yeah, of course you have to. Yeah.
So I'm not talking about the scaling. I'm talking about the spectral pre-processing. Row-wise pre-processing.
Yeah.
So maybe that was the problem with CART.
Yeah, it could be.
I have to be fair.
Do you want to try? Okay, let's do it. No, okay, let's do it in the break, okay? Yeah, you are right, but
I'm always right.
because when you do,
When you do SMV, I mean, I'm thinking if you have these variables and there is one peak, but you have this scattering, or in this case fluorescence effect, you will not be able to maybe find it because there is, look, if you put there, exactly, put all the data. There, the interesting peak is this one. Okay, so
Which
if you
is
take this
this one?
variable,
this one,
no, this one.
this one.
Oh, sorry. This is,
So
so if you don't do pre-processor, you don't remove this baseline. Here you are taking this value, you don't have separation here, so
No.
CAD will not work.
No.
But neither PLS probably, or PLS will see this thing in the 4th, 5th, or 6th latent variable, and that's going to be complicated. So if you pre-process, if you do the SMV stuff without this part, that's important as well. You will see that here you have this kind of peaky stuff.
So we will try later.
Yeah.
Okay. Okay, so if you don't have any further questions, I think we are perfectly on time. I don't know, what is it? Okay, this is okay. And we can go to the next topic, which is, I anticipate you be a little bit more complicated.
Funny.
Funny.